Hello, Mr. Cohen. Can you hear me?
Yeah, I can. Hi, Connor. How are you?
I'm all right. How are you?
Good. Good. You're getting into the fun stuff.
Yeah, we're about there. I feel fairly confident. I want to say I might be a little rusty with the trig equations relative to some of the newer material. So,
Okay.
I've got some examples, but I want to do like one of each and then like high level stuff. So I'll explain more as we go through it, I guess.
Okay.
Um,
And I do have the record on. Apologize for
no,
missing
that's
that last time. I thought I was recording everything, and I had accidentally turned it off, um, but I've turned it back on. So.
That's all right. It actually turned out that last question, if you plugged in those equations, only two of them would have worked, even though it was a double angle formula.
Oh, after I got off the phone with you and I said, I guarantee you all four of those are answers, I decided, what I should do is go up and plug all four of those in and make sure they all work before I go making such statements. And so you did that, and only two of them worked.
Right.
Interesting. Okay.
Right.
I didn't
That's why
realize
it
you
worked
could
out to
have.
be two.
Yeah, I didn't realize you could have extraneous solutions. Like,
I doubt on the well, long story short, I doubt on the reviews it'll be like that. The homework has been tricky because it was formulaic all the way to that end question, which ended up not giving all the solutions that were valid. So
yeah.
I was used to everything that you get as a solution is a working solution, and that wasn't the case in that last one. But
Okay.
that's another issue altogether. So I guess the first problem I have is sine of theta over 2 equals I'm sorry, equals negative root 3 over 2.
And we're just solving for theta.
And we're just solving for theta, right? So um if
Okay.
I'm not mistaken, and this is what I was going to explain when I was beginning this. But so since we have sine and it's negative, we're in the fourth quadrant here, correct?
Yeah.
Let's start
Well,
there.
we can be in fourth or third, actually.
Fourth or third. Okay.
Right.
Okay.
Okay. The way to think about this is think of that as a single angle.
Right. We're going to plug that in. We're going to plug root 3 over 2 into theta, correct?
Well, no, what I'm really going to do is I'm going to take the inverse sine of both sides.
Okay.
And what that's going to produce on the left is theta over 2. And what it's going to produce on the right is minus 60 degrees.
Yeah.
So
Yes.
theta is just 2 times that. In other words, theta is 2 times minus 60, minus 120. Now, go ahead and plug that into your, now hold on, let me think about this. Yeah, if I substitute minus 120 in for theta, then I've got the sine of minus 60, and you should get negative root 3 over 2. Now, did they give you some domain restrictions for this?
No. Not
Because
this
there's
question
also a third
particularly.
quadrant answer. And
Ooh.
in other words, that um, theta over 2, let's go back to here, it's not just minus 60 degrees, it's also 240 degrees. I think I have that right. Yeah.
Ah.
But the
Okay,
problem,
so
yeah, the problem with that is then when you solve for theta, it comes out to be either minus 120 or 480. And then, of course, the 480 you can reduce to plus 120 by subtracting a multiple of 360. And you can either leave that as a negative angle, or you can turn it into 240. So in actuality, if you take the sine of, excuse me, 480 over 2, in other words, this is actually one answer. It doesn't agree with that though, does it? Because if I take 480 and divide it by 2, I get 240, and the sine of 240 is minus root 3 over 2. And if I take the sine of minus 60, I get negative root 3 over 2. Or 300, whatever you want. Minus 60 is the same as 300.
right.
So we came up with two thetas. Now, one of those theta is not inside the unit circle. That one is, but this one is not. So if your domain was restricted to theta being between 0 and 2 pi, then this is not an answer.
Right, okay. Okay.
So you would only have one answer if you had a domain restriction that said that. In a similar way where when we were doing problems where it was 2 theta or 3 theta, where I expanded the domain from 0 to 4 pi, well, since theta over 2, that would actually only go to pi. So the only answers are going to be the first and second.
So hang on, let me back up a second here to catch up with you. Sorry.
Okay.
I don't want to derail a thought, but I want to get to where you're at because you jumped over so let me reflect. When we're doing trig equations like this, we're going to get two possible solutions, right? Because there's in this case, negative root 3 over 2 exists in two quadrants.
Correct. We're going to get always two solutions if theta is in the domain 0 to 2 pi.
Okay, so
and
given
if theta is what we have inside of here. If we have 2 theta inside of there, and the domain is theta is 0 to 2 pi, then 2 theta's domain is 0 to 4 pi.
Okay. So in this case example, I see how we get 300 as well as 240.
Okay.
Because in either one of those angles, that's negative root 3 over 2.
Right.
So when we have both of those angles, we're saying theta over 2 is equivalent to 240 comma 300. And so to get rid of the over 2, we multiply both sides by 2, and that would give us in this case 480 and 300 or 600, correct?
Let's see. We solved for theta over 2, and we got 2 places in the unit circle where that's true. One of them is there, and the other one is there. So we solve for theta by multiplying both of those by 2. So our two answers were minus 120, that's minus 60 times 2, and 480, which is 240 times 2. So the two answers for theta.
Well, I thought if we had.
let me leave it negative for a moment. Those are your answers right there if you were going out 2 unit circles. Let me erase this up here because this is confusing.
Right. We don't have a domain restriction with this problem. This
Okay.
is all solutions. So
Okay. So we're going to
that's one of the
need
more conceptual.
an integer part of this also.
Right. So that's I have the answer solution, or yeah, I have the answer
All right.
solution.
Let's
So
see if we can figure out what it looks
I
like.
just want to tie where we're at to where we need to
Yeah.
go.
So first of
So
all,
I see.
let's move that to a positive angle. So that's 240. So here's our 2 solutions. And I maintain that both of these are solutions. And I can prove it because if I plug in 240 into theta, I've got the sine of 120 degrees. Which is positive.
Because when I look at the -60, that should be 300 degrees, right? If we looked at it in the positive.
Here, let me go back a step. Maybe I can't do this. In other words, maybe I have to live with both of those answers instead of converting it to a positive answer. If you take and plug in -120 for theta, you will be taking the sine of -60 degrees. And that is minus root 3 over 2.
Mm-hmm.
So this is definitely one of the solutions. If you plug in 480 for theta, you will be taking the sine of 240 degrees, which is like a 60-degree angle. It's in the 3rd quadrant, so it's negative root 3 over 2 also. So that being the case, let's figure out what we have here for solutions. I always know that I can... this is where it gets tricky. In other words, I can't, that minus 120, I can't turn that into 240 like I thought I could. Because now when I divide by 2, it ends up in the 2nd quadrant.
Yeah. I mean, I think off the top, the 2 angles, we're working in degrees. So I'll say that the 2 degrees should be 300 and 240. Because that's where sine equals negative root 3 over 2. So I feel like those should be the 2 angles. That's the solution set. I can't. The solution set shows 480 and 600. And so I could see, since you're going to get rid of that over 2 for theta, you multiply both sides by 2, and that gives you those numbers.
Well, let's figure out, in other words, if I believe these are the 2 solutions, or these are 2 solutions, well, I can certainly add 360 to the minus 120.
Mm-hmm.
And that gives me, I can't do that though. Because if I plug that in for theta, I don't get, the equation is no longer a proper equation. This is an interesting dilemma.
Let's see.
So you're adding, you get 300.
So write the least positive non-negative angles for the measure of theta. So it should be 2. Yeah, okay.
What's your answer set?
So the final answer solution is 480 plus 720 in and 600 degrees plus 720 in, where n is any integer.
Okay. We normally use 360 here instead of 720. We're using 720 because it's theta over 2.
Right, that's what I was thinking. Because we're going to multiply both sides by 2, right? If we had...
if it was theta over 3, I'd be using 1080.
Right.
And if it was theta, I would be using 360. So that's interesting. That means that when you're doing 2 theta, you would use 180 instead of 360.
Yeah. Okay. Yeah, that's him.
Now, this one I get. It didn't occur to me right off the get-go that we had to multiply it by 720. But now I see why. And this one is it took that and added 720 to it to get 600. In other words, our solution was minus 120, but because your instructions say only the non-negative angles, then it turns out to be 600 if I add 720 to that. And oddly enough, I guess when you're doing half angles, yeah, you can't just add 360. Because notice if I add 360 to that, I get 240, and then the equation's no longer valid.
Well, so here's how they approached it in the computers program.
Okay.
So the least positive non-negative angles or measures are 240 and 300. So that negative 60, I agree with.
For theta or for theta over 2?
For theta over 2.
Okay.
So then what that would give you is two separate equations, but you'd have theta over 2 equals 240 and theta over 2 equals 300. And this is a follow-up question with sine, but the period of sine is pi or 360, right?
It's 2 pi, but the period of
2
theta
pi.
over 2 is going to be pi, or rather 4 pi. So you got this, right? Let's see. We got
Yeah, so
300 was
240
one of them,
plus
and the other one was 480, right?
240.
Ah,
Those
240.
are the least positive. Those are the least positive. 480 is technically true, but it's not the least positive true.
Is this for theta or theta over 2?
Theta, so for theta over 2, we would have 240 and 300. Now, the way it's worded in the system is it's showing theta over 2 equals 240 plus 360n. And so I think you still have to multiply both sides by 2.
Ah, that's how you get the 720, yes.
Yeah.
And if it was theta over 3, you'd have to multiply both sides by 3. So, okay. Um, let me think for a moment. Yeah, so that's definitely correct for theta over 2, right? If I took the sine of 300, I'd get negative root 3 over 2. And if I took the sine of 480, I would also get, I wouldn't get negative. If I took the sine of 480, that's the same as the sine of 120, which is a positive number.
Right. But right now that is the doubled. So it should be 240 based on the explanation. And then, you have theta over 2 on one side and then 240. So to eliminate the half
Oh,
angle, you
okay. In
multiply
other
by
words,
2.
that's the way it is. Theta over 2 is equal
No, no,
to
no.
240 and 480? No, 480 doesn't work.
480 is the incorrect number there. So it's 300 is correct. 240 is where the 480 goes.
Oh, yes. Okay. Now I'm with you. And yes, the sine of 240 is negative, and the sine of 300 is negative. And normally we would say plus 360 n and this would be plus 360n. And since we have to multiply both sides by 2, that's how we get these two answers. Okay, yeah. That's the way you do it, for sure.
And now I had a question because so I might wait to break this up a little bit, but the the sine of, or the period of sine is always 360, just if we're talking about sine, right?
Yes.
Okay. Okay. And is
Yeah,
it
whereas the period of 2 sine or 2 theta is 180.
okay? Okay.
In other words, if the best way to talk about this is by drawing it. That goes to 360. Okay, and that is the sine of x. If I want to graph the sine of 2x, it reduces the period down to 180. And so I end up graphing it like this.
Okay.
Squeezes it in. And so this only has a period of 180. The sine of 2x has a period of 180.
Okay.
And
That's good. Is that also the
you remember your sinusoid equation where we had y equals a sine of b x minus c plus d? And the key thing to remember is that your period equals b over 2 pi. So, or
okay?
excuse me, your period equals 2 pi over b. So if the sine of x, b is 1, so your period equals 2 pi. But the sine of 2x, b is 2. And so you end up with the period being just pi. Since the period is 2 pi over b, which is 2, period is equal to pi for this. And since we were dealing with 1/2 theta, your period is going to be 4 pi there, or 720 degrees. And that's why each increment to the previous answer was 720. Because the period of 1/2 theta is actually 4 pi. It's not pi, it's 4 pi. If I were to graph on this same graph where here's the 360 mark, and I wanted to graph the sine of 1/2 pi, it would go out to 720. And I would label this the sine of 1/2 pi, or 1/2 x, or theta, whatever you like. But the half stretches it out horizontally by a factor of 2. Whereas if I stick a 2 in there, it compresses it horizontally, just like transformations in algebra did. Horizontal transformations. If this number was less than 1, it stretched it horizontally. If this number was greater than 1, it compressed it horizontally. Works the same way with sine and cosine, and all the trig functions for that matter.
Okay. Okay. Would it differ? Just quick last question. That the visualizing this made it pretty clear to me actually now.
Okay.
So the period of cosine is the same way.
Yep.
The period of tangent, though, is that also 360, or is this different?
It's only pi, and I'll tell you why. In other words, you get the period by how long it takes to restart again. Okay? Here's tangent.
Okay.
Minus pi over 2 to pi over 2 to 3 pi over 2 to 5 2. And tangent goes like this. There's one complete cycle of tangent. And you'll notice that it's pi long. And if I go to my next asymptote,
Gotcha.
it just repeats every pi.
Okay.
And the same with cotangent. The natural period of secant and cosecant is the same as the natural period of sine and cosine, which is 2 pi. But that's how you figure out the period, is when you know, if I'm looking at a graph and I'm looking at something like this, and they say, what is the period? Well, it's the distance between that and that, or the distance between that and that, or the distance between that and the next place where it starts up again, right there. So you can always tell the period by finding the distance between the peaks or the troughs, or the x-axis crossings are a little strange because this is not, that's where it's going down. So you have to find the next point where it crosses the x-axis and it's headed up, which is right there.
Okay. No, that filled it in for me, because the only reason this is going to matter is when I'm if the question is, you know, a half angle, a double angle, and the function is going to be converted to whatever function needs to be.
Right.
So that makes sense to me. So thank you. I'm gonna switch it up here. I don't think I've made you do something like this. So I don't know how well this will work, but this is a how familiar are you with vectors?
Not bad. Vector problems can be really complicated, or they can be relatively easy.
Yeah.
Let me, however, give you the concept of vectors with a real simple problem. It's a problem that illustrates static equilibrium. That's at a 30-degree angle, that's at a 45-degree angle, and there's a weight hanging from this.
Okay, actually it's not good.
If I say that the tension on this part of the cable is 878 pounds, and if I say the tension on this part of the cable is 1,075 pounds. Okay, here's the most important concept that I think I can teach you about vectors.
Okay.
You want to break the vectors up into their vertical and their horizontal components. Okay? So the one thing I know about this picture is that the horizontal components on the tension have to be equal, because nothing's moving. And the vertical components have to equal the weight of that. So if they ask you what is the weight of the object, then you would look for the vertical components of this 878. Well, the vertical component is the sine of 30 degrees. So it's the sine of 30 degrees times 878. And that's 439. And the vertical component of that force, in other words, only the amount that's going down, well, that's the sine of 45. So the sine of 45 times the magnitude, 1,075. And if I do that math, I basically add those two together, and that's got to be the weight, 1,200 pounds. Because I know that the vertical components of both cables have to match the weight on that thing. If that weight was more than 1,200 pounds, then the tension on these cables would be higher. Now, the other thing I know about this problem is that the lateral, the horizontal force, is the cosine of 30. So I can say the cosine of 30 going to the left times that, 878, that is the amount of force going laterally left, and this has to be exactly the same because nothing's moving, everything's static. So that is the cosine of 45 times 1075. And you will see that that number is equal to that number, which it has to be. In other words, when you have static equilibrium, your horizontal components add to 0. This one, you have a left one and you have a right one. So they balance one another out. Okay?
Okay.
And vertically, I've got this component added to this vertical component, and that has to equal that. Because actually the force is up, that tension is on those cables in that direction, and it has to counterbalance the weight. So most of your word problems with vectors boil down to this kind of a thing. Whether if you have an airplane and you have a wind, how do you figure out
the magnitude and the angle is, I think,
and it's all based on the trig functions, on these angles. In other words, if we go back to this airplane and wind thing, let's say I have an airplane moving at 600 miles per hour at a 30 degree. Okay? I can separate that into its vertical and its horizontal speed. Its vertical speed is going to be 300 miles per hour up because the sine of 30 is 1/2. So this is the same force as if I combined a 300 mile per hour force going in that way, and I would take the cosine of 30 degrees to get the direction in that way, times 600, which is square root of 3 over 2 times 600. So square root of 3 over 2 times 600, whatever that comes out to be. So I've now separated my airplane into its vertical and its horizontal speeds. And now we do the same thing with the wind. If we have the wind going along in this direction, at say a 45-degree angle, well, the vertical component of that wind is the sine of 45 times the speed of the wind. Let's say the wind is at 50 miles an hour. Well, that's going in the same direction as my other vertical component. So now I know that resultant is root 2 over 2 times 50 plus 300, and the horizontal component of that wind is root 2 over 2 times 50 going in the other direction, taking away from that speed. So I would subtract it from that speed. And when I'm done, I have a vertical component to airplane and speed, or airplane and wind, and I have a horizontal component to airplane and wind. And now I put them back together again to figure out the resultant, and I get a resultant that it looks like this would be tilted slightly up. So it wouldn't quite be at a 30-degree angle, it would be more of like a 45-degree angle, and it wouldn't be 600. That wind going in the other direction is going to reduce that speed down to, who knows, whatever the resultant you get by combining this vertical with this horizontal.
Okay.
And that is a real basis of working with
Would
vectors.
you care to go over? Yeah. Uh,
We can do a problem if you want.
okay. Yeah, I was gonna
I'll
say.
try.
Um,
Some of these can be, in other words, the problem where I had the two cables and the weight, that problem is made far tougher if they tell you the weight and they ask you for the tension on the cables.
yeah, it won't be that. It's not. None of them are gonna be that involved.
Okay.
The
It's
only
far harder to solve.
the ones that make this well here this is an example, but anyway, so this is a plane has an airspeed of 150 km. Oh yeah, that's fine. 150, we'll say, doesn't matter. It's flying on a bearing of 76 degrees, while there is a 24, we'll just use miles per hour here, so a 24 miles per hour wind coming out of the northeast, a bearing of 225.
Okay, hold on. Let me get my picture down here. The bearing is measured from
Yeah,
the north, right? And you said this had a bearing of how much? 76
76. Yeah,
degrees? So
yeah,
basically
for the
like that.
plane.
There's the airplane. Do I have my picture right?
Okay. Yep.
And what's our wind?
I'm not. They're not giving me a picture.
No,
The
you have to
wind
draw
is
your own
24
picture.
miles per hour.
44
Yeah. Yeah.
kilometers
So
per
I
hour
24, 24, 24
at what bearing?
at 225. So the question asks, what's the ground speed and the bearing of the plane? But that's the equivalent of the angle and the magnitude, right?
Yes, the combined. In other words, you're
Okay.
combining these two forces. And the way I'm going to combine these two forces is I'm going to find out the vertical speed of the airplane and the easterly speed of the airplane. And I do that by the northern speed of the airplane is the sine of 14 degrees times 150. Can you do that on your calculator real quick?
Sine of 14. Actually, hang on. 150 times the sine of 14. 36.3.
I'm just going to round everything off for,
That's fine. Yeah.
okay, and then the horizontal component is the cosine of 14 degrees times 150. And that number is going to be much closer to 150. What is that?
145.
Okay, now that is the airplane. Now let's do
Okay.
exactly the same thing for the wind.
Okay. Okay. So same principle
And
then.
yeah, let's see. The wind was at 225, so this is a 45-degree angle. So the downward speed is the root, it's the sine of 45 degrees times 24. And the westerly speed is the cosine of 45 degrees times 24. Can you give me a number on those?
Yeah. So let's. Oh, because 225 and 45 are the same angle equivalent, right?
Yes.
Okay. Okay. I just didn't know where we were getting for that. So
Yeah, just like I converted the 76 degrees to 14 degrees
got
so that
yeah.
I could work with this triangle here. And that triangle is dependent on that 14-degree angle.
Right.
And
Right.
over here, I'm basically working with this triangle. So I'm trying to figure out this component and this component. And so what do we have for
Gotcha. Okay.
2 times
So
12?
for sine, it's six. It's let's say 17. 17, and then so for
Same for
cosine,
cosine.
it's
Okay?
yeah,
Now,
same.
to figure out the result, I know that the wind is going down, the airplane is going north, the wind is going south, so these are going to subtract. So the net vertical is 36 minus 17. So the net vertical is north at 19 kilometers per hour. And the net easterly direction is going to be 145 minus 17 because they're working against one another.
Mm-hmm.
So 145 minus 17 is 128. So easterly, we have 128 kilometers per hour. And now is all I have to do is combine those two for a resultant. And let me do that by drawing a picture. Where if I had something going 19 miles per kilometer in this direction and 128 in this direction, then this angle let me remember how to do this. Once you get it into a north and a south, yeah, let's see, this angle, I know this is a triangle that's 19, so use the Pythagorean theorem to figure out what that is. What do you get? If you square 128, add it to 19 squared, take the square root of everything. Should be just a little bit bigger than 128.
$129.4.
And theta is the inverse tangent of 19 over 128. In other words, it all becomes trig at this point.
Yeah, no, that's okay. That's it. That's correct. I mean, we rounded, so the answer is actually 130, but that makes sense.
Yeah.
So okay, that's
But
perfect.
the key is breaking everything down into its vertical and its horizontal components.
Okay, yeah, that's clutch.
Realizing that you just add each. In other words, the wind, you break it down, the airplane, you break it down, and you add their northern components, which in this case were going opposite one another. So it's subtracted from the vertical speed, or rather the northerly speed. And the wind was also going against the eastern direction by a little bit, so I subtracted again from that. And the net result is this is the way the airplane would go. It would go at whatever theta is, whatever that angle is now, at a speed of 129 instead of 150.
Okay.
With airplanes, you always have airspeed and land speed. In other words, this actually refers to the instrument settings. They would put the speed of the plane at 150, pointed at 76-degree bearing, but when you combine it with the wind, it ends up being this, only going 129 kilometers per hour at a different angle because of that wind.
Okay. Okay.
But pretty much all vector problems come down to this, where you break it up. And some of them get pretty complicated because you end up with like two equations and two unknowns.
Yeah.
And those are a little harder.
Exactly.
And boy, the book gives you these formulas that are just mind-numbing. And I don't like the formulas being mind-numbing, where they convert it to the unit vectors and all of that. For me, I can understand the problem far easier by just turning it into triangles and drawing a little picture here, and knowing that the wind is fighting both directions of the plane. It's fighting its northern direction and its easterly direction.
Okay.
So I know it's going to be subtract. If that wind was doing something like going that way, then it would be fighting its easterly direction, but it would be adding to the northern direction. So the actual airplane would be going faster than 19 miles an hour in a northern, or 19 kilometers per hour in a northern direction, because the wind is aiding it. I don't know what its total net speed would be. You'd have to do the math. But for me, it's really helpful to work out directions. A classic problem is you have 3 rugby players tugging on a ball, and the ball's not moving. And they give you the angles that each one of them is tugging on and the force that each one of them. This guy's pulling with 100 pounds, this guy's pulling with 150 pounds. How much must this guy be pulling with for the ball not to move? In other words, there is some number that would cause static equilibrium, where the ball would be stationary. All the forces, the left and right forces would balance one another, and the vertical forces would balance one another.
Okay.
And if you know these angles, you can figure out all of the components of those 2 known forces, and then you can figure out exactly what this force must be. But to me, this is a vector problem. Now, in other words, 5 years from now, I remember this type. I don't remember all those formulas that are they have you use.
They don't make them easy. I agree with you there. Okay, no, that's I actually took a screenshot of that problem. That's actually really helpful.
Okay, good.
So that's
good.
I just need a way to understand how to put it into the formula. That's my issue with the word.
And you can see why they can't teach vectors until they teach you trig, because you need cosine, sine, and tangent, inverse tangent, to figure out that angle.
Right. Yeah. So it's more of a way of setting that up into an equation that's tricky for me.
Did they skip by polar? Have you not had polar yet?
I was gonna ask if we could do a polar question next.
Sure.
Okay, so
I figured my book goes polar and then vectors.
I'm doing this by priority.
Okay.
For what I need most. Polar was the last section we went over, so it's the most fresh in my mind.
Okay.
So that's hence why I'm doing it this way. So let me see of a 1, because I want it to be something. Actually, hang on. I know a question.
Okay.
So this is taking a polar coordinate and converting it into a rectangular equation.
What's the polar coordinate?
Or equation is r equals 2 cosine theta plus 2 sine theta.
R equals 2 cosine theta plus 2 sine theta?
Correct.
Just like that? And we're converting this into rectilinear. Okay. So there's a couple of identities that you need to remember with polar. And that is that R is equal to x cosine of theta, because the cosine of theta equals x over r. So if the cosine, oops, I got this backwards. And that's why I drew it, because I wanted to make sure I didn't get it backwards. x is equal to r cosine theta, and y is equal to r sine theta. And you can always tell by drawing that picture, because this is always r, and that's theta. So the cosine of theta is x over r. That's how you get that. And the sine of theta is y over r. That's how you get that one. You with me? Okay.
Yeah.
So in solving this problem, there's a third identity here. Let me just write real quick.
I was gonna say, I think.
And that is that r squared equals x squared plus y squared. Okay?
Okay.
So how do we change this? Well, let's try. There's a little trick that's not obvious, but is used quite frequently here. And that is where you multiply both sides by r. Okay? And that gives you r squared equals 2r cosine of theta plus 2r sine of theta. You with me?
I'm with you.
That's
Yeah.
equal to x. That's equal to
Right.
y.
And that's equal to y.
And this is equal to x squared plus y squared. So what I end up with is x squared plus y squared equals 2x plus 2y. And so there's the rectilinear equation.
And
But they also ask you what it is, right?
okay, so that is the finished. Right. That's finished as it is. Is that correct? Because that's what my teacher has it as.
You
That's
have
the
to
correct.
figure out what shape that is. That's a circle.
Okay.
Okay, and here's how you figure it out: is you have to do this.
Yeah.
And complete the square.
He didn't do that. Okay.
Okay, all that's equal to 0. And now I need to add a 1 inside there and a 1 here, which means I need to add 2 to the other side. And now I've got x minus 1 quantity squared plus y minus 1 plus 1. Well, hold on.
I think it should be minus though, right?
Yeah,
That should be minus.
That's a minus. So y minus 1 quantity squared equals 2. Well, that is a circle with radius 2 with its center at 1, 1. So that's this with a radius of 2.
Gotcha. Okay, so I went and completed the circle. My teacher actually left it as what you circled or squared right initially there.
Yeah.
Just that right there. But that doesn't actually give you the coordinate, the rectangular coordinate. So I didn't see that as a complete answer.
What was the entire question?
It's
convert to rectilinear, and was that it?
Yeah, convert the following polar equation into an equivalent rectangular equation. So I guess that is the equation.
That's an okay final answer. Yeah, okay. That is a rectangular equation.
Real quickly, because this I completed this square when I learned how to do this. That's what I was shown, because I recognized this as a circle because x and y are squared.
Right.
So why does the 2 go on the other side there, right? When you did that first step of completing the square?
Because when I added 1 to complete the square, I can't add 1 to the left side without adding 1 to the right side.
Oh, okay.
Balance. Okay, you always have to do that when you're completing the square. In other words, if you want to maintain it as an equation, then you need to make sure you do to the left what you do to the right, or in this case, that you do to the right what you've done to the left. And I added 1 there, and I added another 1 there, which is 2.
Okay. Okay. That makes sense. Yeah, that makes
And
sense.
then once I get it in this format, I recognize the equation of a circle, the conic section. And a lot of these polars will convert to a conic section. Sometimes a circle, sometimes an ellipse, whatever it ends up being. Um, it just kind of depends on whether they ask you to do that part of it. If they just want you to convert it, this is fine. That is a rectilinear equation.
Okay. Noted. Um, all right, perfect. Actually, so that makes me feel better because he didn't. I went to complete the score the squares or actually give a coordinate, but that's not what he was asking. So that makes sense.
Right, right, right.
So last thing I want to finish off with, I guess, is just to highlight because I didn't find vectors minus the word problems too difficult, and same thing with polars.
Okay.
Um, but generally speaking, if these trig equations are asking for all solutions,
Mm-hmm.
that's just going to be a case if it's either double or whatever the number is from a double angle and half angles. It could be greater than 2, obviously, but that's going to include all of those, correct? So like if a sine problem gave us 2 potential answers and we're going for all solutions, if it's actually 5 of theta, that's going to give us 5 times as many solutions.
Yes.
Yes. Okay.
That's
Okay.
why, let's just take a real easy one here.
Yeah, we can.
Give all solutions to that. Okay? Well, if I take the inverse sine of both sides, I get 2 theta is equal to, let's see, 30 degrees and 150 degrees. And then if I add 360, it's also 390, and it's also 410, and I can just keep adding 360s. Okay?
Mm-hmm. Mm-hmm.
Which means that those are the solutions for 2 theta. Which means the solutions for theta are each of these divided by 2. So it would be 15, 75,
Yeah. Okay.
195, and 205. And had the original problem said, well, make theta go from 0 to 2 pi, this is where people get in trouble because they only come up with those 2 solutions. No, they wouldn't. They'd get all of them because I came up with these 4 solutions, which are between 0 and 4 pi, which is the actual domain of 2 theta,
Right. Right.
0 to 4 pi. And then when you divide
Right.
all of them in half,
But
you end
not
up
in our
with
domain
4
restriction.
angles that are all inside of 2 pi. And that's the only way you get
Right.
those 2 angles. Most people, when they make a mistake here, they'll get the 15 and they'll get the 75 thinking they've got them all. But because they only went out to 2 pi, had they gone out
Mm-hmm.
to 4 pi, they would have gotten those 2 solutions, which gives you those additional 2 that are inside the unit circle. So, and you can apply that philosophy all across the board. If that's a 3 theta, then I got to go from 0 to 6 pi. If that's a 5 theta, I got to go from 0 to 10 pi. And that's
Right.
why,
Okay.
even
Okay.
though
And
theta
and
is inside 1 unit circle, you end up with 5 times many answers.
right. Okay. I'm with you. So the last thing, and just to confirm, I guess, is that if it's asking for all solutions, right, depending on what the problem is, if it's I think in the case of what I'm working with, it's either going to be double or half angles. So it's just going to be not asking for solutions, but it's going to be like what I did with that first problem. It'll be
Yeah,
360
if there's
times.
no restriction on the domain, then I just keep adding 360 to each one of these. So,
So yeah, just adding pi, right?
yeah, so
Of
your
2 pi.
solution would be theta equals 15 plus, plus 180K? I think so. Does that give you, that gives you the 195. In other words, it gives you that one, it gives you that one, and then the other solution is 75 plus 180K. So,
Yeah. So
because on the other problem, when we were doing half theta, we had 720K. In this problem, we're dealing with 2 theta, so it's going to be 180K.
So I have to remember we're working with the period,
and that would cover
so it's actually
all
going to be half of what the period is normally. Gotcha. Okay. Okay, cool.
Okay. Connor, you good to go?
Mr. Cohen, I appreciate the time. Yeah, I think so. I mean, I feel good about this one.
I will process this. I will put it on YouTube, and I will send you a direct link to it.
Okay.
It takes an hour or two to process it.
All right. Yeah, no worries. It's the section of actual trig equations when we did this last time, that section was very difficult. The problems are much harder than what they are in the vector and polar section.
Well,
so very tough.
That's good to hear, because for me it's the other way around. I find vectors to be difficult.
The word problems, I definitely agree. Yeah, I definitely agree.
Yeah, the straight vectors where they're adding vectors or multiplying or whatever like that, those are pretty easy.
Yeah,
when they get into this defining a vector as a unit vector, and then there's certain physics problems where how much force and how strong of a metal frame do you need to support this weight. Some of those can get pretty tough.
Yes, I agree. That's why I wanted to go over a word problem.
Yeah. The ones we went through today are relatively easy because they can all be solved by just breaking the forces down into their x and y coordinates, and then adding all the x coordinates together, adding all the y coordinates together, and then coming up with a new resultant, which is always just the Pythagorean theorem, like we did on our airplane problem.
Yeah, no, that's, like I said, that it was helpful to visualize it. My teacher teaches it how to break it down algebraically. So you're basically getting things into vectors, and then you do the same process with finding the magnitude and the angle that way.
Right.
But it was actually nice to look at it as triangles. I think that's helpful, and that's where I struggle, is visualizing the problem to such a way to tackle it. So that was helpful.
Good.
So with that, Mr. Cohen, I thank you. I appreciate the time. I will be not hitting you up this coming week. Obviously, it's Thanksgiving and all that, but finals, the true finals is when I return from.
Okay, that's fine. And I'm not going anywhere for Thanksgiving, so that doesn't affect anything for me. So
yeah, okay. Well, it'll be December-ish. I think that I give you another.
Are they giving you a whole week off for Thanksgiving?
Yeah.
Oh, yeah. That's nice.
It's nice. I mean, they call it a week off, but I still have homework and stuff that's due that Monday back. So I don't know exactly.
I don't know if that counts as off or not, especially when you're taking most of it online in the first place.
One of my problems with school is that that's another story. But anyway, I appreciate the time as you're going.
Okay.
Have a good Thanksgiving.
You too. Talk to you next time.
Okay, bye.